I'd like to go through these 3 examples, which I think will be helpful. All right, let's find our way back to our seats. So I have 3 more examples that we didn't, I kind of knew we wouldn't have time for yesterday, but I'd like to show them to you now. I think the homework last night was okay. Am I right? I don't know. I'll come, maybe once I'm done going through these 3 examples while you're working, I can come check your homework. They weren't too bad. Some of the ones on here, though, are, well, I don't want to say bad, but a little worse, maybe, in terms of difficulty. And I'm referring to the ones on the back of the sheet that says improper integrals / Maclaurin-Taylor series practice. And don't be intimidated by the name. I'm not sure why we titled it that. That's actually an appropriate title. It's just we haven't started using that language yet for this kind of series and these kinds of problems. So, but on the back of that worksheet, you're going to find some problems that I think right now are a little above our pay grade. So let's look at a couple that are similar to that, so that you're going to be able to do those tonight. Okay. So this one, let's start with this one, for example. This is, I think, of the set of 3 I'm going to show you, the most similar to the ones we did yesterday. So do you remember our technique from yesterday? When we look at this, we're trying to make this feel like A1 over 1 minus r, right? Okay, right now it doesn't look a lot like that, except for the fact that it's a fraction. Oh, that's good, at least. So maybe A1 is 3 or something, but what about this 1 minus r here? Any suggestions? There are actually a couple good suggestions that you could take on this. So I think I hear you say factor out like a 5 on the bottom. Oops. And maybe the game is up then. So what's the first term then, if you're thinking about it that way? Huh? All right, so maybe we don't have to go any further on this problem. Maybe we can see that this will be similar to the previous problems. I don't know. We can write it out, but I mean that was the interesting part of this problem, right? Is like, can you get it in the form where you can recognize like what's A1 and what's R? You know, so but it's not too bad now. So this is a very useful technique to be able to kind of do some algebra and then just use our geometric series results. So we'll write it out. You guys seem to like starting at 0, so we'll do that. 3/5. The common ratio is x to the n. Let's just make sure that makes sense. Let's write out the series. If you plug in 0, you get 3/5. Plug in 1, you get 3/5 times x. This seems to be working. And the place where this converges, since the common ratio is just x, that's not an interesting question here either, so we'll just write that. Okay. Second of my 3 examples for today, this one. Now, this one, definitely doesn't look geometric. In fact, if I were to ask you, could you write this in the form like A1 over 1 minus r, you'd be like, no. And you'd be right to say no. I think that would be not possible. So there is a hint, though. And this is one that you'll take on some of the problems on the back here, too. What does it say? Why is it asking you to consider what it's asking you to consider? What is f prime of x? Yeah, so you see that this is not going to be tractable, but this is. That's very nice. In fact, we can write this out in a couple ways. Maybe we want to write it out in long form, and then we can also write it out as a tight summation notation. So what is it? It's just 1. What's the common ratio here? It's not x. It's actually negative x. Okay. So minus x plus x squared minus x cubed minus the plus dot dot dot. Yeah. Or if you want to write it in summation notation, it's this. Keep in mind that all of the things we're right now doing are not actually answering the question. But we'll get there, right? But certainly, let's just change the question temporarily. Wishful thinking, if this were the question, it would be easy. It's not the question, but if it were the question, it would be easy, right? So the sum is what? Just negative x to the n, where n starts at 0 and goes to infinity. And I don't know, maybe we want to write it as negative 1 to the n, x to the n, just to prove that this is in fact a power series, that it is in fact all just integer, but positive integer powers of x. So either one would be okay. I think that might be helpful to see it that way too, though. All of those are good ways of writing that. Okay, but the thing, of course, we desire is a power series for f. So tell me what you think we should do. How did we get from here to here? Yeah, remember the way we got from here to here was to take the derivative. So as we go from here to here, we can integrate. And by integrate, you know that the integral of a sum is the sum of the integrals. So we can just term by term integrate this. So here we go. Go ahead. X, very good. Yeah, 1/2 x squared plus how's this feel? Do you like that? Or you can do this however you like. If you don't want to, I just want to show you what's happening, because I think that if we were just to do this in summation notation, it would be uncomfortable for you. You don't have to do any of this here. You can just do it all in summation notation. We can actually take this expression and integrate it using just the power rule. I might actually integrate this expression. This is part of the reason I decided to write it this way, besides just proving that it is a power series. We have x to the n. And out here, keep in mind that that, friends, is just a constant, isn't it? It's a different constant for different values of n, but it's just a constant. So we have what we have here is a constant times x to a power. And keep in mind that the derivative, the integral that we're taking is with respect to x. So the integral of that, look at this expression here, is x to the n plus 1 over n plus 1. I'm just looking at this expression right here. This, because it's just a constant, regardless of the value of n, it's just a constant, just comes along for the ride. But this over here is the thing I'm integrating. X to the n plus 1 over n plus 1 is the integral. And that bears out in what we see here. Now, I do have, we'll put n equals 0 to infinity here as well, just like we had up there. And then I think that, let's just make sure this does in fact give this series. Does this look good? We plug in 0, do you get x? You get x to the 1 over 1, and over here, negative 1. Okay, so it seems like it's working. Yeah. Okay. Yeah.
So what do you box? Like what part of that question?
Good question. I might box all of this, would be fine. But I mean, this is a fine answer, or this. Now, sometimes it will be very specific in the question. Sometimes it'll actually say, like, write the summation notation for it. Sometimes it'll say, write out the first 3 non-zero terms of power series, something like that. It'll be clear in the question. But it's not super clear in this particular question. Does it say on here? Let's see what it says here. It doesn't. So I don't know. I think if you can do what I've just done, you've proved you have every level of understanding, right? Now, there's one other thing that we won't emphasize too much right yet, but I will say that derivatives of integrals of power series have the same interval convergence. That we'll say that right now without proof. So what's the interval convergence for this one? Well, it was negative 1 to 1. So this one is negative 1 to 1 also. Now actually, that's a little, there's like a tad bit of a lie there. Turns out that it actually converges at one of the endpoints on this, but we won't go into that right now. We'll just use strict inequalities. So that's like a small bit of a lie. It's actually, we can actually have it converge just a little bit at one other little point, but we'll get into that in the coming days. But certainly in the interior, it converges at the same interior as up here. So cool strategy, yeah? Be able to take the derivative? Well, it kind of stands to reason that you might be able to do that in this situation too. Here's another one that right now can't be written very nicely as a1 over 1 minus r. And there's some like this on the worksheet too. But what do you see? You see, just like on the last one, we had the natural log. We said if we take the derivative, we get something that looks like a1 over 1 minus r. But here, it looks like we started with a1 minus over 1 minus r and took the derivative to get something like this, right? Look, this is to the negative second instead of negative first. So what might we do here? Yeah, we might want to integrate this so that we get something, you know, go up or down the levels of derivatives or integrals to get to something that's 1 minus a1 over 1 minus r, something of that form. So here I think we'll take the hint. Let's integrate this. So I'll write, it's a little sloppy to write this, but we'll go with it right now. We'll write that. We can clean up some of the notation in a minute, but let's just do kind of a general antiderivative. We can maybe discuss the role of the constant. But what is the antiderivative of that, first of all? It's kind of nice, isn't it? It's just 1 over 1 plus 2x. Oh, because the 2, wait, I need to 2 over. Wait, what about the chain rule, though? I think I was. Yeah, I think maybe it's just that. It's just all check mentally. 1 plus 2x to the negative 3. Yeah? Okay. Okay. You can think some more about that if you like, but just that's not the necessarily important part. You take the antiderivative of that, and now do you agree that this is of the form a1 over 1 minus r? Okay, so again, this is not the problem we wish to solve, but it is one that will, wishful thinking, let's solve just because it looks easy, and then we'll see if it's useful in solving the problem we actually want to solve. So the first term is 1, and the common ratio is negative 2x, so. In summation notation, we might write, well, we could write negative 2x to the n, I guess. But again, I might, just like on the last one, I might isolate the x part. So we have negative 2 to the n and then x to the n as separate parts of that, right? We have negative 2 to the n and then x to the n. Just so we can emphasize here that we have a power series in x to the n, in x. The plus. Yeah, so I think it's important to maybe say, I said we're going to skate over that detail right now. But yeah, so technically we'll have like a constant here. But in a second we're going to do something that will eliminate that constant regardless. And that's what? We're about to differentiate anyway, and so yes, there's a constant, but in the end it's going to be gone because we're about to differentiate back again. So I think we're going to be okay there. There's definitely more to say about that story, but let's just look. But I think that's a sufficient explanation for now. So sorry, not f prime, but as we take the derivative of this, we get f. We recover f, which we already said, hopefully, right, is negative, is the thing we want. 1 plus 2x to the negative second. Right, that's not a surprise. That's why we did this whole thing. But now let's do, again, the derivative, because derivatives are linear. Derivative of a sum is the sum of the derivatives. So we can term by term differentiate this. So here we go. That was exciting. Negative 2, 8x, or again, you could just, if you trust yourself with this algebraic manipulation, just take the derivative of this expression. And I have something to say about this too once we do it. Let's just take the derivative of this expression over here again, just because we now know, again, negative 2 to the n is something complicated, who knows what it is, depending on n, it's something different, but regardless, it's just a constant, right? So when we're differentiating with respect to x. Just use the power rule again, but this time we're taking a derivative. So we get negative 2 to the n, that's just coming along for the ride up front. But then here we get what? X to the n minus 1 times n minus 1, yeah? Oh, I'm sorry, n. Now, there's one other thing I want to add to this little piece here. What happens when we plug in n equals 0 to this? Essentially. Yeah, so in some sense you don't need to start at 0. And by the way, you saw that happen right here. The first term just goes away. So you can actually start this at n equals 1, if you like. And I hope you see that that's really that's the same series. Now again, is that a power series? Is that all something times x to a power, where the powers are all positive integers? Yeah, right? This is as complicated as this is. It's still just a number times x to a power, right? So that's, and we should maybe give the radius of the interval of convergence too. So when, can we just by inspection say what that is? For 2x, when is that between -1 and 1? We need x to be between, yeah, in absolute value less than a half. So I don't know, in terms of boxing things, I might box this. How's that for a box? You like that? Okay. All right. So just know that you're going to encounter some of those on here as well. As far as homework goes, just for the sake of time too, I don't want you to have to do all of this. The other one is just practice on comparison tests. Why don't we work on this worksheet? I'll check that tomorrow. It's the one that I was just talking about. Okay. Had you already done the other one? Okay. Yeah, the other one is certainly good practice too. I think it'll be, you could do it in just a few minutes too. So eventually I'll maybe check that one as well.